So please do now. Use this function and answer these questions. Pause the video and then we'll go over it together. So for the first one, I just use power rule and I just use these guys right here, and I put them up front, multiplied them to get what I get right here. So 3 times -1 is -3, and then we change the 3 to a 2. 2 times -3 is -6, and then I change the 2 to a 1. And 1, derivative of 1 is just 0. Let's move on to the next one. Plot f of x and f prime of x on the same screen. Let me get that going for you. Alrighty, so I'm not exactly a big fan of filming me using this, but I am a big fan of using the graphing calculator. Alright, so we have negative, yeah, that's correct. Negative x to the 3 power. And then, man, I'm really bad at typing stuff. Minus 3x squared. And then minus 1. Now, before graphing it, what kind of window am I looking at? This is clearly going to be, it's not going to be a parabola, it's going to be a weird S. It's going to be like an S that's rotated 90 degrees. But what I do know is I do want to have negative, okay, I definitely want to have a negative x because it's going to be significant on both sides. Alright, so we have a little thing. So let's go ahead and do the other thing. The derivative was negative 3x squared minus 6x, and graph it. Alrighty, there you have it. That's what it looks like. So let's continue with the next one. I'm going to go ahead and get rid of this. We don't need this anymore. I'm actually going to see if I can just delete it. Boom, delete it. The next question is asking, for what values of the derivative is the graph, what is the actual graph doing at the derivative and it's positive? So I'm not good at reading. So let's go ahead and get rid of what I just created. There you have it, all nice and clean. So when the derivative is positive, we're talking about these areas right here. And at these areas, what we notice is the graph is going up. And then when the derivative happens to be negative, like at these areas, we notice the graph is going down. So you see that the graph is going down when the derivative is negative. The graph is going down when the derivative is negative. So there's a trend I'm noticing, and there's also going to be a question that's asking like what happens at the zeros. When you look at the 0, what do you notice about it? Well, the actual graph has a local maximum minimum. That's actually also what we call the points when the derivative is 0, critical points. So if you have a local minimum, or just like a minimum, at -2, which is a 0, and we have a local maximum at 0, which is a critical point as well. So local maximum 0, local minimum at -2, and that's because the derivative equals 0 at those points. So let's try to answer these questions after looking at the graph. So again, a lot of erasing that I must do. Come on, come on, come on. I know you're thinking, Mr. S, are you going to go back and edit out when you like erase stuff? No, I'm not. I'm not going to edit that out. That's like the best parts of the video. Alrighty, so what happens when f prime equals positive values? We have an increasing y. So the actual function increases. For what values of x is f of x decreasing? Well, we talked about it. It's decreasing when the derivative is negative. So that will be -infinity to -2, not including those points. And then, here's what I mean. -infinity to 2, and then 0 to infinity, not including 0 or infinity. Okay, for values of x is f of x decreasing. I just mentioned those. For what values of x does f prime equal 0? What feature does the graph of f have at these values? These are local maximums or minimums. And it happened to be 0 when I looked at the graph. Seemed like that was a -2, and it seemed like that was a 0. Alrighty, let's move on. Displacement, velocity, and acceleration. Oh, as a physics teacher, I'm so excited. Students will identify whether an object is speeding up, slowing down by reading the graphs of the velocity. Fantastic, let's do it. We have some definitions that I want to see in your notes. Displacement, what's a displacement? It's a change in position. It's a vector quantity. It means that it could be negative. And the absolute value, or the scalar part of it, is called distance. So distance, you don't say, hey, what's the distance between the school and your house? You don't say -10 meters, you know? Distance is always positive. It's an absolute value. So that's a scalar quantity. Scalar means something that is always positive. Velocity is also a vector quantity. It's the rate of change in position of an object. This is a vector quantity as well because you could have a velocity that's negative. The absolute value of it is called speed. Acceleration, a rate of change in velocity of an object. This is also a vector quantity because you could have a negative acceleration. And yeah, we already talked about this in class. We talked about the velocity. When you have like a derivative of a displacement, we call that velocity. And acceleration will be the derivative of the velocity, a second derivative of displacement. Makes sense. I mean, if you take the derivative of displacement to get velocity, then you take a second derivative, another derivative of the displacement, in order to get acceleration, given that acceleration is a derivative of velocity. That was so much fun to say just now. Alright, I want to see this in your notes. This is a very good picture of what's going on. You always go from, if you go from regular function to derivative, that would represent your velocity. If you go from, and that, by the way, that's if you're for the position. I'm a little confused on why it says speed instead of velocity, you know, because the derivative of a position graph would actually be velocity. You can have negative slopes, but I digress. And then if you take the derivative of a velocity graph, not a speed graph, you would get acceleration. And then we have here a little example. We are seeing I'm guessing this is a velocity graph given the units. Pay close attention to units, meters per seconds. That tells me it's a velocity graph. Yeah, a velocity is speeding up when it has a positive slope. And the reason why we know that is because in order to speed up, you have to have a positive acceleration when you have a positive slope. On the flip side, if you have a negative velocity and a negative slope, you're speeding up again. It just means you're getting faster in the negative direction. So whenever velocity and acceleration agree, they're both positive, then you would speed up. Whenever velocity and acceleration agree and they're both negative, we are speeding up. But if you happen to have a positive velocity, we know this because it's above the x-axis, and a negative acceleration, they're fighting. They're fighting each other. So that's why you would have a slowdown, and the same thing is happening right here as well, for the same reason, because acceleration and velocity are not the same sign. And that just reiterates what I'm saying. Like if you have the same sign, that tells you that we have the speed up, and if you have opposite signs, it means that you're slowing down. When the same sign, the sign is only giving a direction. So positive is not very different from negative. It just means one is right and one's left. So if the acceleration and the velocity are both negative, that's the same thing if, as far as speed is concerned, speeding up, as when you have a acceleration velocity being positive. Alrighty, I hope I said it correctly. I forgot what I said earlier. So if acceleration and velocity are positive, that's the same thing as if they were both negative when it comes to speed. Alrighty, see you guys tomorrow.